Live in the troposphere, bottom of the atmosphere. All Earth's weather happens here in the troposphere. We love the atmosphere, keeps us safe and warm down here. 5 layers tier by tier in the atmosphere. Warmer than the air below, ozone layer had a hole. Airplane contrails white like snow in the stratosphere. We love the atmosphere, keeps us safe and warm down here. 5 layers tier by tier in the atmosphere. Never see a shooting star, the mesosphere is where they are. Coldest layer on Earth by far in the mesosphere. We love the atmosphere, keeps us safe and warm down here. 5 layers tier by tier in the atmosphere. Molecules extremely hot, radiation ions brought. Space station for astronauts in the thermosphere. We love the atmosphere, keeps us safe and warm down here. 5 layers tier by tier in the atmosphere. The exosphere is way out there, nearly space, it's such thin air. Satellites are everywhere in the exosphere. We love the atmosphere, keeps us safe and warm down here. 5 layers tier by tier in the atmosphere.
Hello guys, this is your video notes on characteristics of atmosphere. So as you guys watch the video, pause as needed to fill in your guided note sheets. You will use these sheets throughout the remainder of the unit when looking at items involving the atmosphere. So begin with your aim for the notes. So how do scientists describe the composition of the Earth's atmosphere? Alright, so number one, let's start out with what is meteorology. And meteorology is the study of the atmosphere and the processes that cause weather, which include things like cloud formation, lightning, wind movement, as well as all the other stuff like rain, snow, that kind of stuff. Alright, so what is the atmosphere? So the atmosphere is simply a thin layer of gases that surround the Earth. They are made up of a mixture of chemicals and compounds, which we refer to as air. So that would be the common name, what we call the atmosphere, the air. There's lots of different stuff that's within it, but simply put, we refer to it as air. So the atmosphere protects us from harmful solar radiation in the form of UV light. So there's a special layer of the Earth's atmosphere that we'll get to shortly that talks with you exactly what that layer is. All right, and it also helps moderate global temperatures. So this goes into global warming. So global warming on its own is not bad. If it didn't happen, then Earth wouldn't occur on Earth as we know it. But it does get a little excessive when we add to the natural process of global warming. All right, so what is the atmosphere made of? Well, the most abundant elements in the air are the gases nitrogen, oxygen, and argon. So those are the three main parts of the atmosphere. And here's a breakdown showing the percentages. So the atmosphere is 78% nitrogen, 21% oxygen, 0.9% argon, and then 0.1 other elements. So this would be like elements that there's just very small concentrations of. And there's a variety of those, and we'll look more at that later. All right, so there are several processes interacting to maintain stable amounts of oxygen, carbon dioxide, and water in the atmosphere. So if you look at the graphic here, this is obviously showing you the oxygen or the carbon cycle, where you have CO2 being absorbed from the atmosphere by plants, and then plants breathe out oxygen, and then H2O here evaporates or transpirates from the trees or the plants. Here you've got cows. They release carbon dioxide, but they're taking in oxygen, and then again evaporation is happening at this level. Not necessarily from the cows, but again they do excrete urine, so there is some of that there. And then you have precipitation or rain. This would also include snow. And then here you have evaporation of the water. All right. So this is just another graphic illustrating the hydraulic cycle, otherwise known as the water cycle. So you have transpiration that happens from trees. That's the water is taken up from the soil and evaporates through the leaves or the pine needles, depending on what type of tree it is, and that's just a natural part of it. Step 2, you have precipitation or rain. Step 3, you have a combination of runoff, which would be like water going along the top of the ground. Then you have the water being absorbed into the ground and going into rainwater or groundwater here. And then eventually that makes its way to the sea, where it is evaporated, and the whole cycle continues. All right. So there's those items that we mentioned. All right, so where did these gases come from? So we've talked about the origin of the Earth and all that. So where exactly did they come from? Well, 4.6 billion years ago when the Earth formed, the atmosphere consisted mostly of H2, which is hydrogen, helium, and NH3 and CH4. So, just for reference, this is ammonia and this is methane. So that was not very good for us. So, and this is kind of like a history of how the Earth's atmosphere came to be what it is today based on what we just talked about. So, that spammed up pretty quickly. Well, we'll go through it. All right, so volcanoes spewed large amounts of water, CO2, and nitrogen. So, over time, clouds rained, forming oceans, which dissolved much of the carbon dioxide, locking it into sedimentary rocks through various chemical and biological processes, such as seashell formation, and this allowed the concentrations of nitrogen to increase. As life formed, plants grew, adding additional oxygen through photosynthesis, leading to the atmosphere we had today. So this was a very long process. This didn't happen overnight. This happened over hundreds of thousands to millions of years. All right, so that takes us into the idea of particulates. All right, so particulates. So in addition to these elements, the atmosphere contains various tiny solids and liquid particles known as particulates. In other words, very small particles. We also know these as aerosols. Some aerosols are very beneficial. In fact, they are required for precipitation to occur. Can you guess what these may be? All right, so these are the particulates that we're mainly looking at. So you've got volcanic dust, ash from fires, microscopic organisms, mineral particles lifted from the soil by winds, pollen from plants, particles from meteors that have vaporized, in other words, went from a solid to a very small gas particles, tiny salt crystals evaporated from ocean in the form of sea spray. And here's just a little graphic showing you how those particles got into the air. All right, so one of the last topics on this is going to look at atmospheric pressure and how to do the math between it. So let's get started and let's go through it. So gravity holds the gases of the atmosphere near the Earth's surface. So as you get farther up, there's less gases available. In other words, the pressure decreases. As a result, the air molecules are compressed together and exert a force on Earth's surface. This is where we get the idea of atmospheric pressure. Atmospheric pressure equals the pressure exerted on the surface by the atmosphere, applied equally in all directions, up, down, and sideways. So, again, the atmospheric pressure decreases as altitude increases. So as you get higher, like when you climb mountains, it's harder to breathe as you get to higher elevations because the atmospheric pressure goes down, making less oxygen harder to take in. So there is less weight pressing down from higher altitudes, so the air molecules are farther apart, and they exert less pressure on each other at higher altitudes. So this is kind of the background of why atmospheric pressure changes as you change elevation. All right, so as the temperature increases, the atmospheric pressure decreases. So this leads into weather. So when something rains or whether it's not raining, it all depends on atmospheric pressure. So molecules move farther apart when the air is heated, therefore there are fewer particles and exerting pressure on a given area, causing the pressure to decrease. So that's background on why higher temperatures result in lower atmospheric pressure. All right, so let's wrap this up. Cold air is more dense, therefore it sinks. Sinking air has more pressure because, again, it is more dense. The relationship here, as the temperature decreases, density increases, which means pressure is going to increase. All right, so measuring atmospheric pressure. So meteorologists use 3 units for atmospheric pressure, which include atmospheres, millimeters or inches of mercury, and millibars. Here's your conversion factor for your conversions. 1 atmosphere is equal to 760 millimeters of mercury, or 1,000 millibars. The average atmospheric pressure at sea level is 1 atmosphere. So as you go higher, that number gets smaller, and theoretically, if you go lower than sea level, it would increase. All right, so here's just a picture of a barometer. So meteorologists measure atmospheric pressure by using an instrument called a barometer. And here's just a little sheet showing you how to read a barometer based on the scale. So if you look over here to the right, this is zoomed in. All right, so notice in between here, the big lines would be equal to go up in increments of 0.1, and then each of the little lines would be 1/100th of an inch of mercury. Or on this side, you'll notice the millibar side, they increase by 1 millibar for each level. So pay attention to your scales as you are reading these if you are given one on an assessment.